Good morning, Algebra. Today's lesson is going to be on graphing systems of equations. I'm going to try something a little different. I'm going to try to zoom in a little more because I feel like it's been hard to see the whiteboard. So let's try this, okay? All right. So first of all, if you think about it, graphing systems of equations, it just means basically that there's going to be two equations that you graph. And think about it. I'll just use these two pens as an example. In space, if you have two straight lines, there's basically three things that can happen. One is they could cross. Okay, and if they cross, do you see that they're going to cross at one particular point in space? The second thing that two lines could do is they could be parallel to each other, which would mean they would go on forever and never cross. And then the third option is they could be directly on top of each other so that every point matches the other point on the other line. These have names. The one that crosses is called consistent. We call those consistent equations. They're always going to give you one line. Two that are on top of each other we call dependent. And if they're parallel, we're going to call those inconsistent. So furthermore, think about it, and I understand that graphing in algebra can feel like two separate things, but think about what's happening if you have two lines that are defined by an equation, right? And remember that every point on the one line is an x and a y that make that equation true. And every point on the other line is an x and a y that make that equation true. Well, what happens when they cross? The point where they cross at, if you think about it, is the one point, the one x and y, that make both equations true. And that's a pretty handy thing to know. We'll talk about more real-life examples of how that works. So if you graph two equations, they're going to either cross again, not cross, or be on top of each other. Let's just pick two equations. So y equals x and y equals x minus 1, let's say. First of all, those are both in slope-intercept form, so it makes them pretty easy to graph. I'll do a quick graph here. 1, 2, 3, 4, 1, 2, 3, 4. So y equals x means it crosses at 0, the y-intercept is 0, and it's got a slope of 1. So up 1 over 1 or down 1 to the left 1. So you're going to have a line roughly going through there. I'll do the other one in purple. Y equals x minus 1. Oh, I happen to pick one that's going to be inconsistent. It's going to cross there, and it's going to have a slope of 1 also. So it's going to be parallel. So that is, remember what that is? Not on top of each other, but parallel to each other. That's an inconsistent graph. Let's say that I picked y equals 2x minus 1. So now again, you're going to have a y-intercept of negative 1, but now you have a slope of 2. So up 2 to the right 1, down 2 to the left 1. Now your line is going to be going roughly like that. And there you have a consistent set of equations. And the spot that they cross at is going to be 1, 1. Now, why don't we try that? Let's see if this makes both of them true. So here's our x, and here's our y. Stick in 1 here, and 1 here. Well, 1 definitely equals 1. Stick in 1 here, and 1 here. 2 times 1 minus 1 equals 1. So that's the spot where both of the equations it makes them correct. And then, of course, if they gave you two lines that are on top of each other, the equation would look something like this. So y equals x and maybe 2y equals 2x. And when you solve it, you're going to see that you get a line exactly on top of the other one. And that is a dependent situation. So there you have it. There's three ways that two different equations, two different linear equations, can interact in space. They can be parallel, they can be on top of each other, or the one that we're going to work the most with is when they cross. That point that they cross is the spot that makes both of the equations true. Okay, hope that makes sense. Out.